There's a trick to remembering how to graph the secant function. There's going to be a helper function with it. The helper function, you're going to set y equal to, the cosine of x. And how are these guys related? They are reciprocal functions. So that's how you remember. You set the helper equal to y equals cosine of x, and remember, oh yeah, they're reciprocals, right? So why does that help us? Well, it helps us determine when we graph the cosine of x, the x-intercepts of the cosine of x, much like with the tangent, it helps us determine where the asymptotes are. And it also helps us determine where the kind of the minimum values, the relative minimum and relative maximum values are of the little sections of graph you get in between the asymptotes. So here's how you do it. Okay, so we discussed it a little bit ago. Tangent of x is equal to sine over cosine, and we decided that the intercepts, the places where the height of the cosine function is equal to 0, that's where the asymptotes are going to be. Let's graph the function, and it'll be immediately obvious where those points are. So I'm going to start off at a height of 1. I'm just graphing one period. If we need more than one period, you could extend it a little bit. If you need lots of periods, you could graph it on a calculator. And remember what the cosine function looks like. You start at, I'm going to do this as a dotted curve. You start at the maximum height. It goes down, hits the x-axis, goes down to the minimum height, and then back up again. That's the part of the wave that you graph. Right? And so you're essentially plotting these 5 points. This guy, the intercepts, the minimum value, and the maximum value. Corresponding to the hash marks 0, whatever this guy is, whatever that guy is corresponding with that minimum, that guy and that guy. And so what's the period then of the cosine? We know that that's 2 pi, which makes this hash mark 2 pi. Makes this one pi. Just like yesterday, cut pi in half, get pi over 2. Halfway between pi over 2 and 2 pi is 3 pi over 2, which is actually the 3/4 mark of the period. So the secant of x has a period of 2 pi too, same as its reciprocal function. Now draw asymptotes corresponding with the x-intercepts, because those are the values. Since the secant of x is equal to 1 over cosine of x, those x-intercepts correspond to where the secant's not defined, so they correspond to vertical asymptotes. So just draw vertical lines through x equals pi over 2. Got a little off track there. And label it. It is an equation, right? X equals pi over 2. And also 3 pi over 2. Like so. Label it. It's an equation. This is the equation of that vertical line, x equals 3 pi over 2. And it turns out that if 0, 1, so check out this point right here. If 0, 1 is on the graph of the cosine function, it's certainly on the graph of the reciprocal function, right? So this point's actually on the graph of the secant. And if you plot a few more points, you'll realize that as you approach this first asymptote, you get a U shape. Well, half of a U shape, because we're only graphing one period. But if you graph the whole period, you'd get a shape that looks like, if you graph more than one period, you get a U shape. So this section of it between the asymptote to the left of the y-axis and this asymptote to this first asymptote to the right of the y-axis is a U shape. But if you only graph one period, then that stuff in lavender there you don't see. Whoops, went too far. So I'm trying to graph that portion of it. Then in between the asymptotes, corresponding with this minimum value, this if negative 1, if pi negative 1 is on the graph of cosine of x, certainly it's on the graph of secant. And then you get kind of an upside down U shape. If you plot a few more points, you can convince yourself you'll get an upside down U shape in between the asymptotes. And as you go to the right, it goes down forever and ever and approaches this right-hand asymptote. As you go to the left from the point pi negative 1, it goes down forever and ever and approaches this asymptote to the left. Then over here, if the point 2 pi comma 1 is on the graph of cosine, certainly it's on the graph of secant, and you'll get half of a U shape. The other half exists, it's over there, but if it's over here, but if we're only graphing one period, it doesn't get plotted. Okay? So don't think that's what it really looks like. What it really looks like is a U shape. Let's see, from your perspective, a U shape, an upside down U shape. As you go to the right, you're right. Then another U shape, another upside down U shape, and so on and so forth forever and ever and ever and ever. Okay? But the idea is, if you can graph that helper function, the cosine of x, you can remember the stuff in purple, right? The secant function. That's not too bad, is it? Okay. Let's go ahead and talk about the period. Same as its reciprocal function. So it's going to be 2 pi. So all you have to remember is this. Tangent and cotangent have what period? Pi. The rest have period 2 pi. The rest of the trig functions have period 2 pi. So 2 pi is the period. The domain, it's going to be the same as tangent. So I'll let you see what we did previously. Because the denominators, when you write in terms of sine and cosine, the denominator of the tangent function is cosine of x, right? Denominator, when you write in terms of sines, or in this case cosines, the denominator is the cosine function. So the domain it has the same asymptotes as the tangent function. The range, this is interesting. It goes from negative, if you think height-wise, negative infinity is down here somewhere, right? Negative 1 is right here. That would be one interval in the range, right? And then from 1 right here all the way up to, on the y-axis, positive infinity is up here somewhere. So we could combine those two intervals together and say that the range in interval notation is negative infinity to 1. Does it include 1? Negative 1 is what I meant, yep. Negative 1, does it include negative 1? Yes, it does. Then union, what would be the other one? 1 to infinity. Yep. So that's a nice way to write it. If you're not comfortable with interval notation or set builder, get comfortable with it. And then there won't be that language barrier, right? The jargon barrier, I like to call it. Jargon, half of what's hard about math is the jargon. Because math, a lot of math is just common sense with jargon applied.